Hello, my dear students. Last class I explained how to find vertical stress for the strip load, line load, and also for the circular loaded area. Today, let us discuss about vertical pressure under a uniformly loaded rectangular area. Let us take the case of a rectangular loaded area of length 2a and width 2b. This is length 2a and width 2b, and let the reference axis x and y which pass through the center of the area as shown in the figure. This is the center, so x axis which is passing through the center, and also this is y axis. Let the point P here where the vertical stress has to be found of the coordinates x, y, z. Okay, so here this is from here, that is a depth is z, and this is a radius r, and this is z. Okay, so what I have done, I have not considered the derivation, so directly I have given here the formula, final formula. This you remember, that is enough. Okay, so the more common form of a vertical stress under a corner of a rectangular area of size AB is given by in this equation. Okay, sigma z at the corner, that's why it is mentioned C is equal to Q into 4 pi into this whole equation. Okay, there are three terms, 2mn into m square plus n square plus 1 to the power half divided by m square plus n square plus m square n square plus 1 minus m square plus n square plus 2 divided by m square plus n square plus 1 plus tan inverse of 2mn into m square plus n square plus 1 to the power half divided by m square plus n square minus m square n square plus 1, where m is equal to a divided by z and n is equal to b divided by z. So, and also this equation you can write sigma z c is equal to k into q, where k is our influence factor, like how you have considered for the concentrated load and circular loaded area. Using the table you can find what is k. If you have that value k, directly you can use this equation, sigma z vertical stress at the corner is equal to k into q. Okay, so k is an influence factor. Table gives the values of influence factor k. In the above formula, a and b or m and n are interchangeable. Okay, so this equation can also be utilized for vertical stress at a point not situated at the corner of the rectangular but below some other point a, either inside or outside of the rectangular as shown in the figure 1 and 2. So this formula is not only for to find the vertical stress at the corner of the rectangular area. It can also be used for to find the vertical stress at a point which is not exactly or situated at the corner of the rectangular. It may be some other point A, either inside or outside the rectangular. So I will show, and that is in the next slide, that figures. When the point A is inside the rectangle, then the vertical stress at point P vertically below a depth z is given by this equation. Sigma z is equal to q into k1 plus k2 plus k3 plus k4. Okay, this equation can be used when the point A is inside the rectangle, means this case. Okay, if the point is here, that is A is inside the rectangle, then you can calculate using this equation. Sigma z is equal to q into k1 plus k2 plus k3 plus k4, where k1, k2, k3 and k4 are the influence factors for the four rectangles 1, 2, 3, 4. That is this one rectangle 1, this one rectangle 2, and this is 3, and this is 4. Similarly, if the outside the loaded rectangle, here if the point is outside the loaded rectangle, then construct the four rectangles as shown in the figure. The shaded area in the loaded rectangle may be considered to be the algebraic sum of the four rectangles, each with the corner at A. Okay, so now area is given by small a, b, c, d, a, b, c, d, that is equal to a, b1, a, b1 and c, d1, c, d1, a, b1, c, d1 minus a, b1, then b, a2, b, a2, this rectangle a, b1, b, a2 minus a, a1, d, d1, d, d1, a, a1, d, d1 plus a, a1, a, a2. Okay, so this is the formula for to find the area of A, B, C, D. So sigma z at A is equal to sigma z at this point is equal to Q into K1 minus K2 minus K3 plus K4. This is the formula when the load is acting outside the rectangular area. Suppose the load is here, you can find vertical stress at A is equal to Q into K1 minus K2 minus K3 plus K4, where K1 is the influence factor for area A, B1, C, D1, K2 is influence factor for area A, B1, B, A2, K3 is influence factor for area A, A1, D, D1 and K4 is influence factor for area A, A1, A, A2. Okay, so these are the two cases. So you have to remember three formulas here. This is at the corner. Okay, this formula, if it is inside the point A is inside the rectangle, then you have to use this formula to find vertical stress. That is sigma z is equal to Q into K1 plus K2 plus K3 plus K4. If the point is outside the rectangle, then you have to use this formula to find the vertical stress, that is Q into K1 minus K2 minus K3 plus K4. Then let us see this table for influence factors for vertical pressure under a corner of uniformly loaded rectangular area. Okay, so here these are the M values 0.1, 0.2, 0.3 and these are the N values for 0.1, 0.2, 0.3, 0.4, 0.5, 0.6 like that till 1. Here this M values till 10. So you have to take the M value. Suppose M value is 0.1 and N value is 0.1. You have to consider this value like that. This table also it is for the continued influence factors for vertical pressure under a corner of uniformly loaded rectangular area. Okay, so till this N value is only till 1 here and this is 10 and in this it is continued N value 1.2, 1.4, 1.6 till 10. Okay, so if you have this M and N value, you can find what is vertical stress. In this way, you can calculate the vertical stress under the rectangular loaded area. Next, let us see what is the equivalent point load method. This is an approximate method of calculating the vertical stress at any point due to any loaded area. The entire area is here in this method, equivalent point load method. The entire area is divided into a number of small area units and the total distributed load over a unit area is replaced by a point load of the same magnitude acting at the centroid of the area unit. Thus, the distributed loads over the whole area is replaced by a number of point loads situated at the centroids of the various area units. The influence factors of each of these load positions can be found with respect to the point P, where sigma z is to be determined. Here, this is the loading position Q1 and Q2. This point, this is Q3 and Q4. The loads are acting at the different points and you have to find the vertical stress at this point P. Okay, so the vertical stress is given by this equation. Sigma z is equal to 1 divided by z square into Q1 KB1 plus this portion Q1 and KB1 plus Q2 KB2 plus Q3 KB 3 and Q4 KB4, like that till Qn and KBn, depending upon the number of the areas. If all the point loads are equal magnitude Q, then you can calculate using the equation the sigma z is equal to Q dash divided by z square into summation of KB. Okay, if the value of Q is different, then you have to use this formula. If the Q of same magnitude, then directly you can use this equation to find the vertical stress, that is equal to Q dash divided by Z square into summation of KB. So this method is very useful to find the vertical stress, where K sigma KB is sum of the individual influence factor for the various area units. The accuracy of the result will depend upon the size of the area unit chosen. If the length of the side of the small area unit is less than 1/3 of the depth at which the vertical pressure is required, the error involved in the result is within 3%. Okay, so this method also can be used to find the vertical stress method. Here you have to remember these two equations to find the vertical stress.